Thank you very much for the introduction, for the invitation, this fantastic workshop. And yeah, thanks, Lisa, for setting up the stage. It's really nice to have this background. I think it will be really useful. Yeah, please ask questions throughout, and I'll go slowly because it's technical pretty. Okay, so far, we consider, like typical, so this is like very typical lattice statement. I already, like this is, we had to switch to polynomial rings. So there's this RQ thing. But basically we want to prove some linear relation. So like AS is equal to U over some ring, polynomial ring RQ. And together we also want to prove that we have some short, that S is short. So this, one example is coefficients between -1, 0, and 1. Okay, and as we saw in the previous talk, we can only prove that we know some short S. So actually that norm S, there is a norm blow up. And in the previous talk, it was like, from beta to 2B, right? So that's kind of blow up. But say, yeah, it's still relatively short. But also there is this C. So in the previous, talk, it was the gamma. So there is some short C. And such that AS is equal to CU. Okay, so these are these approximate proofs. But yeah, so like, the beginning of the previous talk was about proving such relations over integers, but then we had to kind of, by force, we had to switch to the rings, right? So now the question is that maybe sometimes, for some applications, we want to have more, right? So maybe we want some, equations like AS is equal to U, but over integers. Okay, so we don't want to work over rings. I want to prove such a statement over integers, okay? And then we want proofs exact. So this means that S is really, S really has some coefficients, let's say binary or ternary. So, and yeah, this is very crucial for, for building more, interesting, more advanced privacy preserving cryptography. Like, for example, if we want to, prove, that we encrypted the vote correctly, then of course we want to prove that our vote was, let's say, 0 or 1 and not just between -100 and 100, right? So yeah, so like in some particular settings, we really need to prove that exact, that, S satisfies some exact like norm properties. And yeah, in some cases, we really want to prove stuff over integers and not just over the ring. Okay, but then yeah, we will see that this results in slightly bigger proof sizes. Okay, so the main focus of this talk, because I could try to prove something more general, but it gets ugly very quickly. So I want to stick to something very simple. So I want to prove this linear relation, AS is equal to U over ZQ, and S has binary coefficients. Okay, so like, I think it's a nice example to go through because it's something, some concrete statement. And yeah, I hope that, by introducing the techniques which are used to prove this, you get an intuition how to prove like similar statements, like proving the Euclidean norm and so on. Okay, so because the talk can be, technical, so I'll do these checkpoints, pretty often. So maybe let's start with how can you raise your hand if you're still following? Okay, good. I hope this this number doesn't, fall that quickly. Okay. Okay, so the overview is that I have these two particular kind of tasks to prove. The first one is like a more algebraic, so just proving linear relations. And on its own, this could be easy, right? But then we have this shortness condition. Okay, so my first step is to look at this binary condition and see if I can prove that S is binary by proving something equivalent. Okay, so the first step is the following lemma. So this lemma says that S is binary. So S is an integer vector, okay? And S is binary if and only if the inner product of S together with S minus the 1 vector, so all ones, is equal to 0 over integers. Okay, so maybe I'll give you a minute to think about how you would proceed to prove that. Okay, cool. Can anyone, give a proof at least for one way? Yes.
Yeah, so it's pairwise multiplication for s, and basically it's the quadratic polynomial that's with its roots at 0 and 1 evaluated at s for every index.
Yeah. Right. So yeah, so basically we use the fact that, if just a single integer s is, binary, if and only if s times s minus 1 is equal to 0. So yeah, so the easy way, like the easy direction is, if s is binary, then the inner product holds. That's like super trivial, right? The second, the other way is also easy. So suppose the inner product is equal to 0. And then, yeah, I just explicitly write what this inner product is, right? So the inner product is just, the sum of si times si minus 1, which is equal to 0. And because si is an integer, we use the fact that si times si minus 1 is always non-negative. Okay? If si was 1/2, then yeah, okay. But like we use the fact that si is indeed an integer. And yeah, so if the sum is equal to 0, then this means in particular that each part si times si minus 1 is equal to 0, which means that it's binary. Okay? Any questions so far? Good. Okay, so now I switch to, now instead of proving binary, I want to prove this inner product over integers. Okay, so the second step is that I will prove this inner product over integers by proving that this inner product holds mod q, and I will prove somehow that the norm of s is much smaller than q. But I don't care about the exact norm of s. I just prove, some approximately that the norm of s is much smaller than q. Okay, and so yeah, so from top to the bottom, it's kind of trivial, but from the bottom to the top, we argue that if this equation holds modulo q, and then the coefficients of s are relatively small, then there is no modular overflow in that equation, right? And if there's no modular overflow here, then we can conclude that this equation holds over integers. So that was our next step. So in particular, now I reduced the proving like three parts. So the first one is the linear relation. The second one is the inner product mod q. And the third one is proving that the norm of s is somewhat small, compared to q. And the first part I call the linear proof. The second part is the inner product proof. And the third part, which we will focus on, is we call approximate range proof.
Is it still the infinity norm?
Yeah, yeah. I mean, yeah, but like so far, like, yeah, we will focus on the infinity norm, but like you can also switch to L2 norm.
So assuming S is a binary string, then it's trivially true that the infinity norm is much smaller than Q.
Right, but you need to prove that. So it's easier to prove that it's like relatively small compared to Q rather than proving exactly. Okay, so can you raise your hand if you still follow? Okay, so not bad. Any other questions so far?
I didn't really do the last one in the last talk.
Right. So the problem is, okay, let me go back. So what you end up with in the polynomial ring setting is that you only prove S such that AS is equal to C times U or some gamma times U. So yeah, so that's not the same. Okay, cool. So now I will focus on the third part. Okay. So now I want to prove that the norm of S is somewhat small. And I will use the following observation. Okay, so if I take, or like if I take any short vector B and I just linear combine coefficients of S, so I do the inner product B times S, then B times S is short, right? And that's not even for a random short vector, but that's for any short vector. Okay, so this is like obvious, right? But then let's consider having a large vector S. So like in the context of proof system, just think that, you know, I want to cheat with a large vector S. Okay, so if I had a large vector S, then the question is, okay, so if I'm given a large vector S, then what's the probability that the inner product of S together with B, with some random short vector B is short? Okay, so that's going to be some probabilistic test we will do.
So the inner product here is an integer, right?
Yeah, of an integer. Yeah.
By short, you essentially mean small.
It's yeah, like this number. Yeah.
Right.
Small,
Okay.
Yeah. Okay, so this will kind of give an idea, like, okay, the prover has some S. We want, you know, like the prover wants to prove that S has small coefficients. So the verifier will give out a challenge B, and then the prover has to return the inner product of B and S. And then yeah, if B and S is if B and S is short, then the verifier should be convinced that the prover had the short vector S.
I'm struggling with the sentences. Should it be short vector S? I mean, B is probably should be short in both of them.
So this one is like, you can think of this part as in the soundness argument. If the prover had a wrong witness, so if it was like big, then the probability that the prover cheats by giving B times S where B is short, random short, is small. So basically the first part, just think of it as completeness, and the second part is about like the cheating probability.
Yeah, but should it be S instead of B in the first part? I'm just confused.
S as well as B.
Yeah, but S seems to be an important part. B
Yeah,
needs to be
B
short.
is short.
Yeah, B is always short, but just in the first sentence, do you mean short vector S, but then short vector B? Is it a typo?
S should be short in the first equation.
Yeah,
it has to be short.
yeah,
Otherwise,
yeah.
it doesn't make sense.
Right. So yeah. Okay. Right. So yeah. So in that first sentence, there should be like a short S, right? That's what you mean. Mm-hmm.
Yeah.
Any other questions about the approach? Okay. So yeah. So the idea is that the prover will, the verifier will send the challenge B, and the prover outputs B times S. Okay, and then the verifier checks whether B times S is small or not. Okay, but then revealing B times S can reveal some information about S itself, so we need to mask it. Right. Yeah. So there is still missing S in the first slide, but yeah, suppose in the first sentence that there is a short S. Okay, so if I take if I take a short random vector B and some short mask, then Y plus BS is still short, right? But now the question is, if I am given a large vector S and Y, so S and Y are large, then yeah, what's the probability that Y plus BS gives me a short, integer in this case? Okay, so the strategy is the same as before, but I'm introducing this Y because later on I need to mask the inner product.
Y in the lower equation is not short.
Sorry?
The Y in the lower equation is not short.
Yes. So like when you want to argue knowledge soundness and stuff like that, you can't assume that Y is short. Y is something, but still, thanks to the randomness of B, you can argue that, if the test holds, then S must be short. And Y you don't care actually in the extraction. Should I repeat?
But if Y is large, how can Y plus something be short?
So the thing is that here it's about honest prover. So the honest prover will sample a random mask, short mask, and output Y plus BS. So then this is short. But then in the knowledge soundness, let's say you extracted some S and Y, and you need to argue that S is, you don't care about Y, to be honest. You care about S. And the next lemma will say that if y plus bs was short, then s must have been short with high probability.
Yeah.
And why, yeah, you don't care.
It's computed model or something,
It's computed modular something.
but it doesn't help to control the overflow because there's still something random in
Right.
the.
Was there questions around here? Okay, good. Right, so there is this lemma, which basically says that, for any s. Oh yeah, that should have been mod q here. Bs plus y mod q. But so the norm of bs. Okay, so for random bs plus the norm of bs plus y, the probability that the norm of bs plus y is less than the norm of s divided by 2 is the most 1/2. So what I can, so the best interpretation is that, okay, so these are just some, this is just an inequality. But what I want to say is that with probability at least 1/2, if the norm of s was big, then the norm of bs plus y must have been big. But if we provide bs plus y and it's short, then s must have been short. Okay, I mean, I will give a more general statement and I'll reinterpret it again to kind of understand the idea.
Sorry, based on what you said, I would expect the middle crocodile sign to be the opposite way around.
Sorry?
I thought you said that the norm of S would sort of be like a lower bound in a product of BS and Y.
So I'm reversing the inequality first, right? So with probably at least 1/2. So okay, so suppose that the norm of S is big. Right. Then with probability at least 1/2, this must have been big as well. This must be big.
You're saying that the upper limit is big, but that doesn't stop from what you've written here.
If you take the inverse probability.
Yeah,
then,
you take the
it
inverse probability.
changes.
Right, you're right,
So
okay,
the lower
yeah.
bound of the probability is that,
Okay, yeah, I would probably have to just write it down and then it would make sense.
Right, thanks. So yeah, so if you take the inverse, then you say with probability at least 1/2, if the norm of S was big, then this must have been big. Right. But in the
For all y, for any y.
or any y. Okay, and so maybe like quick proof. So suppose S, I look at the norm of S, and I define the infinity norm here, and suppose the norm of S is some SI. Okay.
Why do you state for some I?
Okay. I just pick, and it's infinity norm, right? So I can just pick the index for.
Okay, now I get it. Okay, sorry, I get the notation now. Yeah.
Okay, so I can write the inner product BS plus Y to be equal to the term I'm interested in, so BISI plus the rest. Okay, so the R term contains Y, it contains all the BJSJ, which are not equal to I. Okay, and then, so the observation here is that by the triangle inequality, one of these terms has to have norm at least the norm of S over 2. Okay, so again, so my claim is that at least one of these guys, these integers, have to have norm at least that. And why is it the case? Because, yeah, by contradiction, if all of them had norm at most less than S over 2, norm of S over 2, then by the triangle inequality, I would get that the norm of SI is less than norm of S. Does it make sense? Any questions?
Looking here, modulo Q.
Down the triangle.
Yeah.
Here.
Yeah. Sorry?
I don't see this with the triangle inequality, but
Right.
maybe if you would write it down.
It's the maximum, right?
I mean, the triangle inequality is that, okay, so you assume the norm of R is this, the norm of R is less than this. Norm of SI plus R is less than this. the norm of Si is less or equal to norm of this plus norm of this.
How does it relate to BISI plus R? Like, because
BI is 0, 1.
Yeah, so this is when BI is right. So yeah, so it's a good point. This is when BI is 0, and this is when BI is 1. Okay, so at least one of these guys must have norm, at least norm of S over 2. And now, yeah, the question is the probability of hitting one of them.
In this lemma, we are not reducing modulo Q.
You do everything mod Q. Yeah, you can put everything everywhere mod Q and then use triangle inequality. And this is important because later on we will, reduce proving shortness to proving equations mod Q. And yeah, that's really helpful.
If BI is a random binary value, wouldn't the probability of hitting that value, the final sentence, be exactly a half?
I mean, at least we know that there's at least one.
Sure.
I mean, there could be two, which is
Right, okay.
better for us.
Sure, okay, that makes sense.
Okay, good. Any other questions? Right, I think there will be like one more, like lemma with a proof, but yeah. So now if I amplify, then I can pick a matrix B, which has lambda rows, and apply the same strategy. Okay. And now I'm gonna interpret this equation again. If the norm of S was big, then with an overwhelming probability, BS plus Y must have been big. Okay. But later on, we will see that BS plus Y must, like if we reveal BS plus Y, if a prover reveals BS plus Y, which has small norm, then we reach a contradiction. So the norm of S must have been small. Okay.
Now for an arbitrary vector Y.
Yeah, for arbitrary vector Y. Because yeah, so the intuition is that what you control here is this randomness of BI, and then the Y is whatever. Okay, so the intuition is, okay, so I will have some, like very dumb protocols for now. So yeah, so suppose I want to prove that the norm of S is somewhat small. So what I do is that I just send Y and S, which is completely useless, at least to give an intuition of the approximate range proof. So let's say I send Y and S. The verifier sends me the challenge matrix B. Okay, and I just reply, I do some rejection sampling. Oh. Yeah, I forgot to mention, but like, yeah, we resolved this issue with rejection sampling in Lisa's talk. So if you, then the slides will be updated. So yeah, but don't care about the rejection sampling. So if the prover sends Z equal to Y plus BS, then the verifier can check that Z is equal to Y plus BS. Oh, I should do it here. And this norm of Z is small. And this the lemma before shows that if Z was small, if Z has small norm, then with high probability the norm of S must also be small. Okay, so that's kind of the intuition on this approximate range proof. Obviously, the protocol doesn't make sense because we reveal everything, but still. Any questions about the intuition? Okay, so now how to make it, less zero knowledge, I guess. So we will use commitments, but we've seen commitment schemes, binding. For now, I'll try to, do some hand waving. So I'll just say we commit, and I'll specify later on what commitment we use. Okay, so the idea would be, okay, I'll just send, instead of sending y and s, I'll just commit to y and s with some randomness. So I just sample some randomness and I commit to y and s. Okay, the verifier sends the challenge B. And yeah, this is still a kind of a stupid protocol because I reveal everything at the end, right? Which is completely non-zero knowledge. So if I reveal, oh yeah, I'll just get back to it. And then if I reveal y, s, and r, then the verifier can check everything as before, but the verifier also checks that the commitments were constructed correctly. And yeah, the argument is kind of still the same. If z was short, then with high probability s must have been short. Sorry, you have a question.
Yeah, I was just wondering, like, you use the same randomness for both commitments. Is that just like an efficient thing?
I guess for simplicity.
Yeah.
But yeah, we will see that
It's not a problem, at least. That's what I'm wondering.
I mean, if I pick a complete commitment scheme, I will have everything under one randomness.
Okay.
I'll just pick a long enough randomness.
Right.
Any other questions? Yes.
Why is the verifier sending the matrix? Like, why is B the matrix and S the non-matrix instead of the, wouldn't it be better to make S the matrix and B the vector?
I mean, the matrix B comes from this lemma that we're using.
Right.
And then, yeah, so we need like lambda rows to make this negligible.
Okay.
Any other questions? Yes.
So previously the rejection sampling was saying that alpha minus the normal bound of the witness was the bound, right?
Yeah.
So this time it's the dimension of this.
Yeah, because I define S to have binary coefficients, and B is also binary. So yeah, if you sum, if you do an inner product with binary,
Okay.
with two binary vectors, then the norm is at most the dimension.
The inner product.
Right, of the inner product, yeah. Yes,
Which norm is it?
infinity norm. Throughout previous talk and this talk, infinity norm. Okay, so now, yeah, now the idea is that, okay, instead of sending these sensitive information, I will just prove knowledge of them. Okay, so now basically I have this protocol, this approximate range proof, and now my next job is to prove knowledge of, all the, of y, s, and r, such that z is equal to y plus bs. And the idea, and that lemma from the approximate range proof allows us to, when I say z is equal to y plus bs, I want to prove that mod q, which will be very helpful. So this, I want to prove this mod q and not just over integers. Any questions?
Just go back one slide. I just want to see the difference again. Randomness. Okay, yeah, okay. I was wondering why there's four things we sent, yeah, but we also need the randomness. Okay.
Right. Okay, so if there are no more questions, then okay. So now I reduce the problem of proving, approximate shortness to proving these linear proofs. I mean, also there is the commitment opening proof, but on top of it, there is just a linear proof. Okay, so then everywhere I just need to prove various inner products. So either between two secret vectors, or like the secret vector with itself, or proving inner product between a secret vector with a public vector. Okay, so yeah, so that was I guess first technical thing. So maybe can you raise your hand if you still follow? That's not okay, not too bad. Yeah. I guess I'll go over this in the second talk. I think it's like more complex, so I think it's worth spending more time on this instead of rushing. Okay, so the next step, as we saw before, is we need to prove inner products, right? So like just quickly, everywhere is just inner products. I need to be able to prove inner products. Okay, and then yeah, if I want to prove inner products over integers, like if I want to work with a protocol over integers, as we've seen in the previous lecture, this results in a somewhat bad soundness error. And that was exactly the reason why we switched to this polynomial ring setting. Okay. So now, ideally what we want to do is that we want to translate the relations, the inner product relations, to some relations over the ring RQ. And then if we manage to do that, then we prove statements over RQ, which give us exponential, soundness, exponential challenge space. Okay, so is this motivation clear? Okay, so how to translate that? Okay, so I have this. I consider the same ring as before. So polynomial rings mod Q modulo x to the d plus 1. Okay. And yeah, we have these nice properties like as I mentioned, we do infinity norm, and there is this lemma which says that if the product A and B, if A and B were short, so, yeah, if both A and B were short, then A times B must also be short. Okay, so take a deep breath. Let's get started, I guess. Okay, so now I will define these weird functions, the automorphisms. So I define these automorphisms, and I will only care about one, which is the sigma minus 1. Okay, so what is sigma minus 1? So sigma minus 1 maps each x. So just to recall, this is the x, right? So I map each x to x inverse. Okay, so that's my function, right? So if I have, I don't know, x plus like x squared plus x, then I define this function sigma minus 1 to be equal to sigma of x squared plus sigma of x, which is x to the minus 2 plus x inverse. Okay, so basically just write your whole polynomial and then swap all these exponents with a minus. Okay. And also for notation purposes, I will define the constant term. This is just a constant term.
Let's see if I'm following. What exactly is x inverse? Is it
right? So it's
a number, or
it's a x inverse mod x to the d plus 1.
right?
So x to the d is minus 1.
Right.
So what is x inverse?
Yeah, what you said, like x to the d plus 1, or no? Yeah, I lost you already. Sorry.
Yeah. So like,
I think when you're asking people to raise their hands, there should be a way to communicate that information to you in zero knowledge. Such you know how many people have raised their hands or not, but you don't know the identity of which.
right.
A novel application.
I guess if everyone raises their hands, then. But I don't think it's gonna happen.
How many are raising their hands under duress, though? That's the question.
Are we saying the function to the polynomials, or like to each?
Yeah. So I
The
define
variables.
So if I do like x squared plus x, okay? Do you see that?
Yeah.
Then I define it as sigma of x squared plus sigma of x.
Okay, so every x.
Exactly. And then coefficients you leave alone. So like if that was a 2, then it's a 2. And yeah, so x inverse times x, what's that? It's probably like minus x to the d minus 1. Right? Does that answer your question?
It does, yeah. I just have to stare at it for a while. Thank you.
Okay, I'm just gonna take your lunch break. Okay, so we have this weird sigma. So now why is it useful? Any questions so far? Yes.
Okay, but I mean, I guess it's important here that X be invertible. And, you know, you might, know where it's not invertible. Right. That never happens in practice.
Is that you would, so you mean like you don't pay x to the d plus 1, right?
Yeah.
Yeah, so whatever technique we want to introduce later, it doesn't translate naturally to other such rings. Yes.
So just to be concrete, like what does sigma do? It reverses the coefficient vector and negates it?
Reverses the coefficient. I mean, apart from the constant one.
Yeah,
Apart from the constant term, yeah, it reverses and negates. Yeah. Yes. Yeah. So
So it's not exactly.
yeah, the constant term stays the same. Yeah. Okay, I mean, the next slide will give a kind of explicit definition. Any other questions? Yes.
Oh, do you only need sigma -1 or do you also need sigma I later?
Just for this talk, only sigma -1, literally.
Do you even use others in the paper?
I mean, in this line of work, no. But like if like early on, there was a, you know, like there was also a sigma 5, which is used to. So there is a fact that, you know, if a ring element is constant under sigma -1 and sigma 5, it's an integer. It's like a result in algebraic number theory. Okay, so let's continue. So now, okay, maybe we went into the details too much, but like the main goal was to prove inner products over ZQ, right? And we want to translate this inner product into some relations over the ring RQ. So how do we do this? Then we have this following lemma. Let's take two polynomials, okay? So I just write them like this way. Okay, so U is equal to the sum of UI x to the I. V is equal to the sum of VI x to the I. Then the constant term of U times sigma of V is exactly the inner product of the coefficients. Okay, so this lemma basically tells us that we can translate proving inner products to proving statements about constant terms. Okay, so what's the proof? Or maybe any questions about the statement?
The U in the polynomial,
Yeah.
the different U's and the U the polynomial, or because it's a different font.
Yeah, I guess just yeah, it's the same
So it's
U.
a vector. So
Yeah,
it's a vector U times sigma.
No, U is just a RQ element. This U is just the RQ element, which I write explicitly like this. So UIs are integers.
Exactly, but
Oh yeah, this is the same. This is the same. Okay, and the proof is kind of simple. So if you just write it out, literally everything, so then U is this, right? U is the sum of UI x to the I. Sigma, well, I just apply sigma to V, and V was this form. Okay, and then yeah, what was sigma? Sigma is I apply, you know, inverse to each exponent. Okay, so this is this step. So each x to the I gets mapped to x to the minus I.
It's just missing a -1, right? Sigma.
You define sigma.
Oh,
Right, I just find sigma to be, yeah, it's
okay, no, I get it.
too much
Okay.
work.
Yeah.
There's only one automorphism in this talk.
The first place.
Right, because yeah, sometimes it's a -1, sometimes it disappears. Yeah. Right, so I have this sum. And then, yeah, I can write this as this sum, right? Sum of all the ij's such that ui vj x to the I minus j. And then if you look, if you now inspect what the constant term is, it is exactly, this will contain all the u0 v0 plus u1 v1 and so on until ud minus 1 vd minus 1. Okay, so like, yeah, literally nothing happened. Yeah, any questions about the proof?
How did you come up with this? Is it like you stare at it long enough and you play with it long enough, or is it some deeper connection from algebraic number?
I think there is. Okay, so like when we wrote that paper, we just stared long enough. Simple, just stare long enough. Yeah, I think so. We have some ongoing, and so we have one work at Asia Crypt where we like look at this trick in other settings, like other cyclotomic rings, and it really goes a bit deeper in terms of algebraic number theory. So this constant term is, for people familiar with, the constant term is related to the trace of an element, and then yeah, there are some tricks here and there, but yeah. Okay. Cool. So this allows us to prove various inner products, and in particular, if I want to prove, so now suppose that S is a vector, of dimension D, which means that I can just plug in, coefficients of S into one polynomial. And proving this inner product is the same as proving that the constant term of this weird guy is equal to 0. Okay. So then, your S, let's say your S is this U, right? And then, this -1, I map this -1 to this vector, which has exactly coefficients, coefficient vector is exactly all the ones.
Just to check, CT now is defined to be the function that plugs out the constant term.
Yeah.
Okay, that makes sense.
There's no reason, right, why you apply the automorphism to S and not S minus 1. You can do it in either.
I think the reason is to make it
Simpler.
Look nicer. But it's really subjective because I could have put just sigma here, right? And then there will be just a single S. Like, yeah. Okay. And then yeah, like if I care about like longer vectors of length m, and let's say m is divisible by d, then I could just split all these s's as subvectors of length d, and I do the same computation here. So right. So all the sj's are, yeah. So basically all the, sj is the j like part of the s. I have these s1 up to sm over d, and I apply the same technique for each component. Okay. But I don't want to spend too much time. Like it really gets ugly now. I mean, that's just the beginning, but. Okay, so we translated proving, things over, inner products over integers to proving things over the ring. So that's good. So back to the overview. I had these things, and now I translate all these things to proving constant terms. Constant term, constant term, constant term, whatever they mean. So yeah, so like here I wrote explicitly what this is, but here I didn't even bother. It's like you can derive all these functions on S. Okay, there will be like some automorphisms here and there, blah, blah, blah. Okay, so basically what I do is that I reduce proving inner products to proving stuff about the constant terms. And these functions fi, they will have these, sigmas here and there, right? Because to get from integers to the rings, I need to do the sigma thing. Okay. Right. So at the end of the day, what you can believe is that, yeah, I transform everything to proving that constant terms of some, functions fi of s and y, because that's the only secret I have right now. I prove that the constant terms are equal to 0. Yes.
So when you're proving like a public, like one part of the inner product's public, are
Yeah,
you just going to like commit to it and just work over the commit?
So if let's say I want to prove an inner product between something public and something secret, I can do that trick with the automorphism. I do the automorphism on the public part. So let's say if I had, U and V is secret. Sorry, if I had U secret and V public, then, like the verify can compute that.
Yeah, sure.
So then, I have my secret, which just doesn't have this automorphism, which is
F still quadratic then, or
yeah. I mean, like for for linear relations, this is linear.
Okay.
Here is quadratic, and here is also linear. But for simplicity, let's say everything is quadratic. Okay, so we switch to rings, and how many people are still following? Yeah, I guess we lost some people, but yeah, I mean that's 50 minutes. I guess we're like maybe 30%.
Why is there Gandalf?
Because we switched to rings. Just for fun. Oh, maybe to wake people up. Okay, so now we want to prove we have a bunch of functions. We want to prove that the constant terms of each of them is equal to 0. So here comes the following kind of observation, which will again have 2 points. So the first one will be used for completeness, and the second one will be used for soundness. Okay. So the first one is that, if I have any integers, okay, if any integers mu1 up to mu k, so suppose I have k such functions to prove constant terms, then if I linear combine, then the constant term is obviously 0, right? If all these outputs had constant term 0, then if I multiply with integers, the constant term is also 0, right? Pretty simple. And if I try to cheat, and for some output the constant term is not equal to 0, if I linear combine, then there is only probability 1 over q to cheat. It's a pretty standard argument. Yes, you have a question? Oh, sorry.
Something I feel like I asked it like another, but can't we also just choose a single mu and then powers of that?
Right. So yeah, we had this discussion, and I think, yeah, maybe for efficiency it could be better, but I guess, yeah, the soundness gets slightly worse.
That was probably also a bit harder to argue, maybe, or something. That's just a k over q then, maybe. Yeah. Okay.
Yeah, some k over q. Yeah.
For a cheating prover,
Yeah.
where does the randomness come in so that it is actually like uniformly 1 over q probability
Yes.
that it ends up to be 0?
These will come from the verifier.
Which one's the muse?
Yeah. So the mutes
Okay.
will be the challenge. So
Right.
the same strategies as in approximate range proofs. Yes, for completeness, for any mu, this holds. For any mu, if you do a linear combination, then the constant term is 0. But if one of the polynomials doesn't have the constant term 0, then if you random linear combine, then what's the probability that this linear combination has constant term 0?
It makes sense.
The mu I can also be 0, or
They are just uniformly random. And then you want to argue the probability problem.
And the reason we have many right is because we're doing row by row of AS equals U.
Sorry?
The reason we're considering many linear equations is because we're doing row by row.
Yeah. I mean, there are a lot of functions here, right? There are a lot of them. Like here is row by row. Here it's row by row. Here's only one, so that's good. Okay, so what we will do is that we will repeat this strategy L times. Now I'll show you how we repeat. Any questions so far? Okay, yeah. So the thing is that sending this, like you can't really argue zero knowledge because, sending the sum can reveal some information about the underlying, about some information about S and Y. So again, we introduce this random mask.
I guess the reason why you would repeat is because Q is polynomially large.
Right, right.
Exponentially large, like in elliptic curve.
Right. Yeah. Yeah. Thanks for this remark. So yeah. So in the lattice setting, Q is very small. Like define very small, but like it's most of the time it's like polynomial insecurity parameter. So usually you need to repeat.
Sorry, I don't understand.
Yes.
How can it possibly leak information? Isn't it supposed to be zero? So what?
Right. So the idea would be to send the whole send the whole term, and then the constant term is zero, but the linear term can. Right. Okay. So yeah. So the idea is exactly this. I will try to mask all the terms apart from the constant term. So what I will do is I will sample, random polynomials which have constant term equal to zero. Okay. And I will, the J will be from 1 to L but suppose J is just 1, simplicity, so I don't repeat. So I do HJ, or like H equal to G plus that sum. Okay, and then exactly this G will make sure that all the other terms apart from the constant term are random. Okay, and the reason we pick G to have constant term equal to 0 is that, if you look at this term, constant term of this is 0, constant term of this is 0. These are integers, so the constant term of H must be 0. But then the idea is that the verifier will send these challenges, and the prover will send the H, which is of this form, and the verifier can manually check whether this H has constant term 0. Okay. Any questions?
The way to check that the G has a constant term 0. The G is sampled privately by the prover.
Yeah. So the argument says that, like for G has kind of similar role as the Y in the approximate range proof. You don't care. Like in the extraction, you don't care what G is. If the prover tried to cheat and have a constant term non-equal to 0, then this randomness will catch that. So that's
What is the current communication complexity? I'm not quite sure what we are sending or what's like, are we sending polynomials or just someone committing? I'm just maybe just
right now you would send all the LHs. So for simplicity, so if your let's say your Q is 2 to 32, okay, then you would create 4 such H to get 128 bits security. So you would send 4 polynomials, 4 ring elements.
Okay, so we need to send vectors. Okay, okay.
So you got a question first.
Yeah, so you're committing to the GIs, and this is why I cannot choose like even if I don't choose constant term equal to 0, then because of the challenge I cannot know how to choose it.
Yeah, exactly.
But then in the end I have to open the GIs in, or
I mean, you open the GIs, but you don't care what they are. Like,
no, but if I open them, you get the information, or
you mean open them like in the later on? So what you do is that you in the honest execution you will commit to the G's. Okay, you get them the challenges, and then you send the H, and you have to prove that this equation is correct.
okay, based on the commitments I sent, the verification algorithm will work, or
Yeah.
You don't open the G itself. You just prove that with respect to the committed G, this
Yeah.
is
Yeah. I prove that G satisfies that.
Yeah, I'm a bit confused about the spaces now. So G are polynomials, right?
Yes.
So on the right hand side, like in the sum, like what are the spaces of these things?
Right. So this is a ring element. I want to prove that the constant term of that is 0.
Yeah.
These are integers.
It is confusion. Okay.
Because if these were ring elements, then it missing.
Challenges.
These are the challenges which will from the verifier. At least that's the idea. I haven't defined the protocol yet. Okay, so the idea is that it's exactly the same as before. So the prover commits, samples these masks, random masks, commits to them using the same R. Then the verifier gives these challenges, the mu's, and the prover gives these H's. So basically the masks linear combinations, so linear combinations of all these Fi's together with a mask. Okay, so it gives all the H's, and then the verifier can manually check whether the constant terms are equal to 0. Yes.
S supposed to be a vector of ring elements. So
Yeah.
how does
Let's say.
But when you wanted to prove the inner product of like of S and S minus 1, when we interpreting S as just one big polynomial.
What's that?
Oh,
I split
chunking it or something.
Yeah, I'm chunking. Yeah.
The elements of S are integers, no?
Sorry?
Yes, there's a vector of integers, no?
I mean, yes, but like at some point I swap to the polynomial representation where I just put all the integers into coefficients.
Yeah.
Can you just explain at the end how the verifier is now convinced again, like why does this really relate to the original S?
Right. So
I think for me it's best to see it on when you show the protocol, like what information the verifier gets, like because yeah, just not quite seeing how this we ensure that these H's that get sent at the end.
You need to prove that as well.
so the next part.
Okay, that's missing.
Yeah,
I was like,
it's
that's
slowly. Yeah.
that's why I was like,
You're going from quadratic to
yeah, I get it. I just thought this was the whole thing, and that's why I was like having okay, this will just come next. Okay.
It's never the whole thing.
Yes, I'll try to finish in maybe 5-10 minutes, but it's like 50%. Yes. Okay, so basically now I reduced it to proving what I have left is I have to prove this equation. Okay, so now the nice part is that this thing here is a standard quadratic equation over the ring. Okay, I mean standard. There are some sigmas here and there. I mean that's there are some sigmas, but overall these are just some quadratic equations over the ring, and I don't care about constant terms or anything. So my goal now is literally just proving, obviously proving knowledge of the opening, but also proving that proving that this quadratic equation holds. Okay, so let me just do one more step and then we can have a lunch break. Yes, so these are just some public quadratic functions, and some of them involve sigma. Okay. So how many people are still following? Yeah, more or less. I mean, if we can get like a overall idea, then I think that's already good. Okay, so like I want to prove multiple quadratic equations. So the idea is that, okay, I'll just linear combine all of them. So I will linear combine. Is this L? I guess, yeah, just that's probably a different L. But basically I have multiple quadratic equations and I'll just linear combine them to get one quadratic equation. Okay, so now I will prove that this one quadratic equation holds. Okay, and then you know, for soundness, okay, so I want to prove that all these pj blah 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 are equal to 0. So obviously, if I take a random linear combination, then this will give me 0, right, for completeness. And then what you can do is that you can again argue about, you know, invertibility, blah blah blah. That if one of them were not 0, then with high probability, this whole sum must have been non-zero as well. Right.
It's been on 0.
Yeah. Yeah. So, yeah. So if one of those is not 0, then this sum with high probability must also be not 0. Okay. And yeah. Here we go a little bit more into the details of the ring, but maybe we don't have to like explain it because like that's a bit technical. But yeah, the idea is that you can pick some moduli for which you can argue that, you know, the probability that an element is invertible is overwhelming. Okay, so even though it's not a field, so not every non-zero element has an inverse, but you can say that if you pick at random, then there's a very, very high chance it has an inverse. Okay, and then you do this to argue that, you know, so if all the pj's gave me 0, then, or like if one of pj's is not 0, then with high probability, the whole sum must be non-zero as well. Yeah, to some argument. Okay, so at the end of the day, we managed to reduce everything to proving a single quadratic equation over the ring. How many people are still following? Yeah, I guess not too bad. But okay, I think that's a good point to stop. Because then yeah, then it gets real ugly. But yeah, I guess it's a good point.